Hello, good morning. How are you doing today?
Good morning. Morning.
Morning, everyone. So today we're doing specific gravity and Archimedes principle. Now, this is the fluid chapter. Usually we do this toward the end of the semester, so I don't think anybody's lecture is fast enough that they have talked about fluid. So we will spend a little bit of time to explain these concepts before we can look at the procedure for the lab. First, we're trying to measure specific gravity of an object, right? So what is specific gravity? Let's start taking a look at the definition for that. Simple enough is simply a way of talking about the density of an object in comparison to water. So specific gravity is simply a dimensionless quantity that is the density of the sample divided by the density of the water. The density of the water is 1,000 kilograms per meter cube. So that's the density of the water. So what is the density of the sample of the object you're interested in? You use that divided by water, you get a ratio, and that's specific gravity. So we use water as a reference because water is used, we know the density of the water, right? This number is easy to memorize. So as a comparison, if your ratio is bigger than 1, you get a specific gravity bigger than 1, you know, oh, this object is more dense than water. So when you put it in water, it will sink. If you get a ratio less than 1, then you know, oh, this density is smaller than water, it will float, right? So that's a way to categorize different objects. So take a look at our pre-lab. The first question is simply asking about the specific gravity of the brass. To calculate that, you need to know the density of the block. So how do you calculate density? You use mass over volume. Okay, so for same object, if you use a smaller mass divided by that smaller volume, you'll get the same number if you had used a bigger mass of the object divided by the bigger volume, because it's essentially still the same material. The material has the same density, no matter if you take a small chunk of it or if you use a big chunk of it, the same density. So once you get the density of the brass, divide that by the density of the water, you get the specific gravity. That's it, right? So we want to measure specific gravity of different objects. So in this lab, we'll measure objects that are dense, more dense than water, objects that are lighter, less dense than water, and a fluid, another fluid. So to allow us to measure specific gravity, we take advantage of a principle that's called Archimedes principle. We will do the derivation later, but first let's take a look at what is the Archimedes principle. So the story usually goes that when Archimedes was thinking about this type of problems, he got an inspiration one day when he steps into the tub and see the water level rises, right? So we all have that kind of intuition. We have that experience that if you immerse an object in water, fully immersed or half immersed, the water level has to rise. Or if you already have a full tank, then in that case, the water will spill because the object takes up some space. The space that were occupied by water now is being occupied by the object that you put in water. So we call the amount of the water that is rising or spilled over is the water being displaced. It was there, but now has to make space for the object, so its water is now being displaced. We also know that when you put something in water, the water will provide a supporting force upward. So that's the buoyant force. Archimedes' principle is telling us, well, this force, this buoyant force, is exactly equal to the weight of the water that is being displaced. So if you have a full tank, right, and you put something in there, water spill, and if you collect that spilled water, that's the water being displaced, and you weigh it, that tells you, oh, this much force is being applied to the object to try to lift it up. So that's the F of B, the buoyant force, is equal to the water displaced. So that is Archimedes' principle. Okay, that's it. Of course, at the same time, the object has gravity, its own gravity. So if the buoyant force is enough to balance its own gravity, the object will stay afloat. If your buoyant force is not is smaller than the weight of the object, then the object will still sink to the bottom because it's not enough to lift it up. Okay, so how could Archimedes' principle help us calculate specific gravity? Well, that we can do a little more play on this density here. So here we're saying, okay, S is rho of the sample divided by the rho of the water. That's the density. But we want to measure weight. Well, that's something is easier to measure, right? So how do you get density to weight? You multiply that by volume, you get mass, multiplied by that G, you get the weight. So you multiply numerator and denominator with the same number. So it hasn't really changed the equation, right? You just simply multiply them by the same volume of the sample times little g. So rho of the sample times volume of the sample becomes the mass of the sample times g becomes the weight of the sample. The denominator, what does that become? That is the weight of the water of the equal volume as the sample, because you multiply by V of the sample. As we said earlier, that is the water that's being displaced, because if you put an object of this much volume in the water, the water need to make space for the object. So the water being displaced will have the same volume as the water, right? This much big. So that's the water being displaced, which is also equal to the buoyant force acting on the sample. So you can see from this step to this step is where we use the Archimedes principle. So to measure specific gravity, now it really requires us to measure two things. One is, what is the weight of the sample? Well, that's easy to measure. We'll put it on the scale, we read the mass, you can get the weight. The denominator is the buoyant force when you immerse the object in the water. So, okay, so how do you measure how much force is the water is lifting up the sample? Well, we know that if you weigh the object in the air, it's gonna give you a reading. And if you put it in water, because the water has lifted up, so if you weigh the object, it's going to give you a smaller reading, right? So we can get the buoyant force indirectly by weighing the object in air and in water 2 times. The difference will become how much supporting force is provided by the water. So that's what we're going to do. So we're going to weigh the object in air, that's easy, and weigh the object in water. So specific gravity becomes W in air divided by the difference of the weight in air versus in water, and that is the buoyant force, right? So for part A, you can choose a variety of different solid, and I recommend that you include brass in your table, because later on you will have to refer to the results in part C using the brass. So it makes sense if you just read the brass as one of the 3 different choices. So that would be a little bit easier, save you some time. Okay. Also, in terms of treating the units, be very careful. We read all of our scale give you unit of grams, okay? And I do have a table here to you have to show explicitly what the weight of that is. But in terms of the calculation, there is actually a shortcut. So I want to show you how it works by going to the pre-lab. Okay, so for example, if you did your measurement and you have an object, it has 7.2 grams is what you read on the scale. That's the mass in air, and in mass when fully immersed in water is smaller, is 4.5 grams. So to calculate the specific gravity, you use this equation. That's what we just talked about. So you can see our devices give us the mass, but not the weight. So to use this equation, you would do this. You would say weight in air minus weight in water. So the weight in air is the mass times little g, mass times 9.8 meters per second. So you got to change it to kilograms first and then multiply by the gravitational acceleration. So this will give you the unit of newtons, right? That's the SI unit. And the same being repeated for the weight minus the weight in air, in water is 4.5, 10 to the negative 3 kilograms, and multiplied by little g. So that's how it goes. But in terms of your calculation, you could do a shortcut because you realize they all are grams, so they all cancel, right? The little g they all cancel. So this is the same as using its mass directly. So the mass in air minus mass in water. So this is your specific gravity. So you it's really just 7.2 divided by 7.2 minus 4.5. Okay, so when you do calculation, you can just do this. You don't have to calculate all of that. So that's a shortcut, but you need to know why this is okay, because all the units and g cancel out so that you can use your mass directly. So that's how I want you to show in your data sheet, is that you want to show explicitly what the weight is by converting it to kilograms, and 9.8, this is in the unit of newtons. You do not have to finish this calculation. You can just give your number like this, okay? In terms of calculating specific gravity, you can go to what I just talked about earlier, use the mass directly, okay? So that will give you S, which is a dimensionless quantity. Okay, so that's part A. When your object is more dense than water, you can simply immerse it in water and read the number on the scale directly. Let me go ahead and find our video and we can take a quick look at our data collection for part A.
Professor,
Yes.
for the specific gravity, like where the arrow is, do you want us to actually solve that equation or also just leave that one as well?
Oh, for this, yes, you do have to get the number.
Okay.
Yeah.
And then for the in water weight, do we also use the 30.4 times 10 to negative 3 times 9.8?
Oh, the weight of, wait, here? The
Where,
weight in water?
yeah, yes.
Yeah, so weight in air is the mass in air times g. Weight in water is the mass in water times g, right?
Okay.
We're not doing the weight of the water, not here. Okay, so let me get my video to come up. Okay, so let me shift this share to my video and we'll take a look. So this are all the various objects it gave you, and you only need to pick 3 of them to record your data. Actually, the video, they only did 4. So you're just picking 3 out of the 4. They, before part A, they did a preliminary analysis to verify Archimedes' principle. So just to demonstrate that is actually true before you use it. So to do that, they So this is a block, and to get the volume of this aluminum block, they measured the length, the width, and the height. And you can see if you use length times width times height, you get the volume of the block. They also put it in water and read the volume by how much water has been rising up. You can simply ignore that because you will get the volume by using length times width times height. So you don't have to worry about putting it in water. So that's the mass of the aluminum block in air. And that's the mass in water. Of course, when you immerse in the water, you cannot let the water cup sit on your scale, right? You have to support it. Just the object itself is. So with that preliminary data, you could verify Archimedes' principle by plugging the equations for the buoyant force. And believe they have already showed you the weight difference in air and water. That's the buoyant force. You want to see if that's indeed equal to the weight of the water equal volume. So you can use the volume of the block, that is the water it displayed, times the density of the water times little g. So that's the amount of weight of the water that's being displaced to show that these two are indeed equal. That's just a really quick check of this principle before we use it. So part A is where they measure different solids. Graphite, that's the first material they measured. You can record the mass in air is about 6.9 grams. The mass in water is smaller, about 2.9 grams. And they did aluminum, and they did the sort of a lucite, the plastic thing, and then they did the brass at the end. So I do recommend you record the brass as one of the objects. The reading for the top one is kind of blurry. So the mass of the brass in air is 34.4. Because if you have trouble reading that, that's 34.4. The mass in water is 30.4 roughly. So that's part A. With that, we are able to use Archimedes' principle to calculate the specific gravity of these different objects. And you might wonder, well, couldn't you also just use its own density divided by the density of the water? Of course we could. So as a check, you could try to verify your results by simply just calculating its density directly, because while we measure these objects' dimensions, and we can find its volume using the formula, and we can find the mass of the object by putting it on a scale. So mass divided by volume give us the density. And can use the density to divide by the density of the water is specific gravity of the material, right? So this is sort of a check of your results using Archimedes' principle. You can measure the density, calculate it directly without Archimedes' principle, or you can use the Archimedes' principle, which was what they were showing you earlier. So part A has actually two parts. The first part is you use Archimedes' principle. The second part is to do a check, simply using the dimensions to calculate the density of the objects. Part B is something that's less dense than water, and they used a cork. You can see that funny thing about the cork is it's going to float in the water. It's not going to sink, right? So to make the cork fully immersed in water, we will have to add a heavier object as a sinker so that you can drag the cork down. But you can see that you do not want this heavy object to play any difference in the measurement. So the measurement only involves the cork in air versus the cork in water. That's the only difference. The sinker remained in water for both cases, so that we controlled for the sinker. The sinker is not going to affect your result. So for part B, in order to measure an object that's less dense than water, you're going to do the reading 3 times. One is the weight of the cork in the air, and you look at the reading to get the mass of the cork in the air, where the sinker is in water. And then weight 2 is both the solid and the sinker are fully immersed in water. So that's the difference between these two, is one is in air, one is in water. So that's the cork. This is the cork. So if you get a difference in the reading, you know that extra difference comes from the buoyant force acting on the cork. Okay, the buoyant force on the solid, the sinker, is not going to make any difference here because they're both in water for W1 and W2. So to measure that, let's take a quick look at our video. Okay, so that's the second part of part A, where they do the dimensions. Let's go to part B. Okay, I know that is also hard to read. So that's the mass of the cork in air. That is 2.1 grams. Okay, so we have trouble reading that. That is cork in air, but sinker is immersed in water. This one will give you W2. Wait a minute, hold on. Did I did this very quickly? Okay, W1, okay, W1, the cork is in the air. Sinker is always in the water. So cork in the air, you read 26.4 or 5. It depends on how you want to interpret this. 26.5 grams. W2 cork is now in the water. Now you can see it's lighter because you have the buoyant force, and that's 18.4. That is W2. Actually, at mass of 2, but you know how you could convert the mass to weights. Should we change millimeters to centimeters or meters? That's a question I get. To calculate its density, now if you want to compare the density to the density of the water, which was given as 1,000 kilograms per meter cube, so you need to keep your units consistent with that. So if you are giving a millimeter, yes, you will have to change that to meters. Okay, so you have to multiply a millimeter reading by 10 to the negative 3, 0.001. So that is meters. Yes, so you have to change that to meters, which means the grams will be converted to kilograms. So you get a density that is in the unit of kilograms per meter cube. That's for the second part of part A, that you do have to do that conversion. Okay, so that is our part B. Before we do part C, let's take a back at our slides of the theory. So you might wonder, okay, how do we measure specific gravity of a liquid? Now, for a solid object, we can immerse in water. Now, for a liquid, we need to use a sort of a modified method. We cannot put a liquid in water, but we can put a solid object in water and the liquid. So they both will provide a buoyant force on the object. And depending on the density of the liquid, they will provide a different amount of buoyant force, right? So we take advantage of that to help us calculate the specific gravity. So let's take a look at the derivation. The specific gravity definition is the same for the liquid, is the density of the liquid divided by the density of the water. If we multiply the equation by the volume of the liquid times little g, numerator becomes the weight of the liquid, denominator becomes the water of the weight of the water that has the same volume as the liquid. So if we immerse the same object in liquid, in an unknown liquid, let's say alcohol, and we immerse it also in water, we can make sure that the displaced liquid and the displaced water is the same volume because they all come from being displaced by the same object. So we can use Archimedes' principle by saying, well, the weight of the water being displaced is simply the buoyant force of the material acting on the material. And the weight of the liquid is simply the buoyant force provided on the solid when you immerse it in that particular liquid. So you can see that this helps us translate the calculation of specific gravity to simply weighing the same object twice. Once is weighing it in water, once it weighing it in liquid. So the weight in air minus the weight in water is the buoyant force the water provides. The weight in air minus the weight in this unknown liquid is going to be the buoyant force the liquid provides. So you have translated the original equation to this modified equation is, well, you can simply weigh the object in air and put it in water, weigh it, and put it in alcohol and weigh it. In this case, we use alcohol, right? So in the lab, they actually use the alcohol. And let's read these three different things. So you can see they use the brass. So the numbers you have recorded for the part A, the brass, where you put it in air and you put it in water can still be used here. So they used alcohol. The only new measurement you have to take is to immerse the brass in alcohol and read on the scale. And that's 31.1. 31.1 grams is the mass of brass in alcohol. Previously, you had already read the mass of the brass in air, which was 34.4 grams. And you also recorded the mass of the brass immersed in water, that's 30.4. So qualitatively, will you be able to answer, well, if you immerse in water, it reads 30.4. Now you immerse it in alcohol, it reads 31.1. So which liquid has a bigger density? Is it the water or is it the alcohol? What do you think? So you put it in water, it gives you a smaller reading. So it looks like the water provided a bigger buoyant force on the object, right? So that's you read less on the scale. So does that indicate water has a bigger density or smaller density than alcohol? What do you think? Water has a larger density than alcohol. Very good, thank you. Indeed, because the buoyant force is the density of that liquid, whether it being water or the alcohol times the volume times G, right? So from here, you can already see and predict your alcohol will have a smaller density than water. The specific gravity of the alcohol will be a number that's smaller than 1. And if we do the calculation, we can see that it turned out to be indeed smaller than 1. So that's the reading you have just see in the video, right? These two are carried over grams from the previous step, so you don't have to measure it again. The one that's new is 31.1. So you can see that if you do this calculation, and again, show what the weight is, but in terms of calculation, you can use a mass directly. The mass in air minus the mass in the liquid divided by the mass in air divided by minus the mass in water. So this is going to be 3.3 divided by 4. Okay, so that gives you 0.825. There is also a quick check to see our calculation by measuring the specific gravity using a hydrometer. This is a device that's already been, so the mechanism has already been built into the device. So you can read the specific gravity of a liquid directly. The device already give you the scale and tell you what it is. So we do this as a check. We'll show you that at the end. Use a hydrometer. So they simply just pour some liquid, in this case, the alcohol, into a cylinder and then put the hydrometer into this liquid and it will tell you what the specific gravity is. So they tell you to read it at meniscus, that's the lowest, the bottom of your water. So you don't read it at the edge because at the edge it tends to be a little bit higher than the bottom. So read it at the center. And this is a little hard to read. The specific gravity, you can see this, the hydrometer has a scale, 0.8, and then at the bottom you have another scale that's 0.85, right? It looks like right now the liquid level is exactly in the middle of these two. And that scale is not labeled, but we know it's halfway between 0.8 and 0.85. So that is 0.825, which is similar, pretty much the same as the one you have calculated using Archimedes principle. So that's the last part where we measured the liquid of the specific gravity of a liquid using Archimedes principle. Okay, so and that concludes all we need to do for this lab. So do we have any questions so far?
For the thing that you just showed us, is that going in the box to the right, and do we just write one of them?
This one?
Yes.
Yeah, the one you just read directly, that blue thing, that's your 0.825 is what you measure using the hydrometer. Yeah.
Okay.
So calculated here, right? This one what goes here. You can compare these two.
And then are we also doing it for the water and the alcohol?
This is the specific gravity of alcohol.
Oh, I thought, okay, I see. I misunderstood.
In this case, the liquid being the alcohol, right?
And then the weight is just the mass times the 9.8, correct?
Yes. So because technically we're still using the weight, right? But the calculation, we do a shortcut by using the mass because we know all the other things that cancel. But I want you to show that we actually know how to calculate the weight. Okay.
For each time we do the weight, do you just want us to write the calculation like every single time, or do you want us to calculate it ever?
You do not have to calculate the weight. Just give what the weight will be. Showing your units is enough. So like what I showed here, you just need to write it. You don't have to say, oh, what the calculation of that is.
Okay.
Any other questions? Yeah, what exactly is the density of the water? Standard, we just simply use 10 to the power 3, 1,000 kilograms per meter cube. It's like the 9.8, sometimes we use 10. So we're just gonna use 1,000. And also knowing that for different water is going to measure slightly different density. Because water could consist of different minerals, and that will affect your density a little bit. So, but the standard in our calculation, we simply just use 1,000. Okay, 10 to the power of 3, 1,000 kilograms per meter cube. Any other questions? Also, it's nice to use 1,000 is sometimes if you change your unit to grams per centimeter cube, you can see a kilograms is 1,000 grams and 1 meter cube is 1,000 centimeter cube. So if you use grams per centimeter cube, then your density of the water becomes 1. Okay, 1,000 becomes 1. So it's 1,000 kilograms per meter cube, which is equivalent to 1 grams per centimeter cube. So it's simply easy to remember. That's also another reason why we use 1,000, not the 997. Okay, now that's all for today. I do want to remind you, you have a quiz today. I will send out a reminder on your Canvas. So quiz 3 covers 3 labs, including uniform circular motion, and the rotational dynamics and static equilibrium, those 3 labs for today. So make sure that take some time to do your quiz later today. Okay. All right. Okay, so if you do think of any questions later on, feel free to email me, and I will see you all next week. Bye, everyone. Have a good rest of your week.
Take care, Professor.
Thank you. There was a question from Brian. Is there no density? I don't quite get that question. Density in the air. Density is simply just a intrinsic property of the material. It doesn't change where you put it. You put it in the air, you put it in water, you can have the same density for that object, right? Does that answer your question? Okay. All right. See you everyone.